Hello and welcome. This is the second part of a three-part series on Proteus tutorial, more specifically on filtering. So in this topic, you will be able to learn how to make passive filters, and you will be able to make use of the graphical representation for the signal output. First and foremost, we need to generate our signal, and in order for us to do this, we need to make use of the tool found here. This is what we call the uh, generator mode, and when you click this one, you will be able to look, or we will be able to see the different kinds of signals. So in this case, what we're interested is we are going to make use of the sine signal, because this is what our topic is. So to start, we can click here in the screen. So here, this is now our signal generator. It can provide a sine wave signal. And in order for us to change the characteristic of that signal, you can just left click this one. And you will be able to name. So let's just say sine gen. And we can change the amplitude, let's say 5 volts. And we can also change the frequency into 5 or anything that you want. So here we can just say phase time delay is empty, or you can choose phase. In this case, we'll just make 0. So once you're finished, you can, okay. So this signal can then produce that characteristic. In order for us to check whether this signal is correct, we can make use of a load. So let's just make a resistor for our load. So we can click here. Then we can place there also the ground line here. So we can attach this one to there. So you can check the signal coming in. You can use AC voltmeter to check. And if you simulate this one, you can see that the AC voltage is fluctuating. Okay, but in order to really appreciate this sine wave, it's much better if we represent this one into a graphical form. So how will we do that? So we stop first. We will delete this one. So in order for us to make use of a graph, what we can do is first let me complete the circuit first. Ground line, connect this. Then the next thing is, in order for us to place it in a graph of the signal, is you can make use of this probe node. And since we are measuring voltages, you can use these voltages. And you are going to place here, because we want to know if the signal that goes into this resistor will have what we have preset. Now, we don't place it here in the bottom because that is ground, so we can expect that the signal generator there is 0. So after you place there a probe from here, then it's time to make use of a graph. So click here, graph, and you are going to choose analog. The reason why you are going to choose analog is because this signal is an analog signal. So click on the screen, drag, and click. So this will be your graph. Let me adjust this one in the corner, and let me adjust this one. Okay, so if we are going to check, so we're going to add this signal or to the analog analysis or the graph. So to do that, you can either right click this one, right click and add trace, and you add this R11. But to make it much simpler, you can just click, hold, and drag it and place it to the screen. Yeah, so like that. So from here, you can simulate the signal. You don't need to press play. In this graph, it will analyze the circuit for you. So you can just right-click, simulate graph, or you can just automatically press paste to run the graph. So as you can see, this is the graph. So from 0 to an amplitude of 5 volts. And in 1 second is our display. So we can see that when we set the sine gen, we set it as 5 cycles. It means that there are 5 frequency, 5 hertz. So it means that there are 5 cycles in 1 second. Okay, so we can adjust the time, the stop time in this graph. Okay, so to generate filters or to make filters, I think the most basic filter or basic passive filters are low pass filters. Now, there are lots of ways to make low pass filters. You can make use of RLC, RC, RL. No. But in this case, for an example, we will be using RC, resistor and capacitor. So how do you make a low pass filter? Basically, what you are going to do is, or the circuit looks like this. Let me delete this part. Now, I need a resistor and I need a capacitor. So the circuit looks like this. Then I need a ground line, and I'll touch this one. And the output of this one is usually in this part. Okay, so that's the output into the ground. So let me, oops, share again. Okay, so from here, I can just, let's delete this one first. Let's delete the trace, and we can drag again this trace. Okay, then we can set it, run it. So we can see that there's no difference. But if we change the values, let's say for example, this one, by the way, mistake. So if we click this one, we can set it, let's say for example, 1 microfarad, run it. You can see that with that change, we can see that the signal is offset, or there is a change in phase. No? So we can check also, let's say for example, if we are going to compare this one signal to our sine gen, we can click on this, click, you can place it there, then run it. So we can see that the signal is very small here compared to the signal of what we generated. So we can reduce this signal, we can reduce its resistance so that there is a higher value or higher amplitude. So let's say for example, we make it 10. Then click that, press that one, so we can see that the signal is some sort of shifted. Now, in order to really appreciate these signals or these low-pass filters, it's very hard to look at it in the time domain. So it's very difficult whether this low-pass filter is working or not. So in order for us to do that, then we can make use of another graph. So let's go to graph. Then there is what we call frequency. So we are now in the frequency domain. So we are going to check the gain and the frequency of the circuit instead of the time and the amplitude. Okay, so to do that, you can click on the frequency, then drag again, drop. So this is now a frequency domain. You can click on this, place it there. Then from here, we can space. You can see that we can't see it. But if we change the value, let's say, for example, this is 100, this is, by the way, I forgot that you need to set the reference value to the sign gen, because since we are using decibel, it requires the voltage output over voltage input. So therefore, your voltage input should be referred. And we can also state here the starting frequency and the end frequency. So let's just make stop frequency at 10 M. Then okay. Then from here, we can press space. So we can see here that since this is a passive filter, we can see that the signal cannot uh, produce gain, but instead it is attenuated. But if you are using, let's say, an active filter, and therefore you can use it, you can use op-amps to place there a gain. But in this case, since this is just a passive filter, then we can expect that then there is always attenuation. So here we can see that one is the gain is 0. It means that the input is similar to the output. No. So there is no gain because this is in the decibel. But by the time we are in higher frequency, the attenuation is increased. Now, the main point of having a low-pass filters or creating a low-pass filters or designing low-pass filters is to make it na siya ni. No? The best type of filters is that there are ni in which it's not sloping. So to do that, let's say, for example, if we change this value to one end, we can expect that we can see that from a frequency of 1 to around 1 megahertz or around 100K, we can expect that the lower frequency is still accepted. However, once it reaches a point, the attenuation is greatly increased. So it means that the lower frequency is accepted, but the higher frequency is attenuated. So this is a good example of a low-pass filter. Now, let me delete this one. Another type of filter is the high-pass filter. So high-pass filter. So in high-pass filter, it's quite the opposite with the low-pass filter, in which lower signal is attenuated while low signal is attenuated. Low frequency is attenuated while higher frequency is accepted. So in order to do that, I can just inverse this one. The circuit for a high-pass filter is just the opposite. So we can just exchange these two circuits. So let's do that. So we can delete this one, delete this wire, delete this wire, delete this wire, delete this wire. We will rotate this one, then we will also rotate this one. So, okay, so click on this, click on that, connect this one, drag this one here, connect this one to the ground, then we are going to probe this one. So this is because this is the output. So we can click, drag this one here, we can delete the other one. Let's drag it again. So drag this one. Okay, so here let's try to view the signal. We can see that the signal is at lower frequency, it's attenuated, but in higher frequency, it is accepted, or the gain is increased. No? So it means that all higher frequency has the similar input, is similar to the signal generation input to this circuit. Okay. So again, a good circuit or a good filter design, it should be, there should be a higher steeper, then there should be a knee, a greater knee for that one. So let's say, for example, let's change the value to 1 megafarad. Okay, maybe this one will change the. So if you click this one, we can see now that there is a knee, a steeper angle. It means that lower frequencies is really attenuated, but higher frequencies are accepted. So this is an example of a high pass filter. So the next one is a band pass filter. So in a band pass filter, it's basically a combination of the low pass and the high pass. So since we are in the band pass, it means that a certain band is accepted. So the sides is removed while the center is accepted. So again, it's like a combination between the low pass and high pass. So if you have this one, we want this signal, then also we want the other one to go down. So it's just a combination of the two. So to do that, we can use similar circuit. So let me change this. We can combine the circuit again. So let me, delete. We move this, delete this wire. We move this one there. Connect. Then we're going to attach a low pass filter here. So to if you create a low pass, we need a resistor there, and then we will have the capacitor. We have it there. Okay, then we connect this, then we connect this one to the ground, and the one that we're going to probe is no longer here, but in this side. So we click on, we're going to check for the signal. So let's try to view the signal. So you can delete this one, add this, and we can, so we can see here that we can see the bend. It means it's attenuated in these frequencies, but we can see a slight bend here at the beginning. So it is attenuated at some sort of lower frequency. So if we really change, or if we really want to see the circuit, we can change this one to the same thing that we did in the previous one, 100, and I think this one was 1F. Okay, so let's try this one, and we can see it is much better. We can change the start frequency to around 1 milli, and we can also see this one. Let's make this one 1G. Okay, so we can see it in the graph. So here we can see that in these frequencies, it is attenuated, but in certain frequencies, it's accepted. And in some higher frequency, it is also attenuated. Okay, so this is an example of a band pass filter in which one specific signal will only pass. So a specific frequency will only be passed, or similar to the input. Okay. So finally, we will have what we call the band stop filter. Okay, so a band stop filter. So in a band stop filter, it's basically the circuit. I will make it a circuit. So this is how the circuit looks like. Usually the circuit will have, instead of here, let me rotate this one. Let me just add another resistor. So usually it is parallel to that one. And this one, you will have that resistors or setup. So if we are going to run this one, we can see that we cannot see the rising here. So let's try to adjust the values. So we can say that this is, let's try 1 nano. Okay, then in this one we can say 10K. We will also make use this one 10K, 10K. And also this one is, let's check this one to 1P. Okay, 1P. Picofarad. By the way, I made a mistake. This one should be placed here. So we're going to probe that one, not here. No, so click, let's drag this one. Let's delete the other one. And then we are going to play. So in this graph, we can see that a specific signal is, our frequency is attenuated. So it's around somewhere around 100K to 10, close to 10 megahertz. So here it's accepted, meaning it's similar to the input, but in a certain frequency, it is closed, and another certain frequency it is open. Okay, so this is a example of a bandstop filter. So as you can see, this is an example. All of those circuits are example of a passive filter. So in the next session, we will talk about active filters, and one of your activities is considered as an active filter.